First, dear Chairman, ladies and gentlemen, dear audience, first of all, I feel similarly greatly honored to be here and present to you some of our work from the lab. I'd like to take you a small lab tour. Maybe it will be a little fast. It's like a crash course. Yeah, I have a bad reputation. But yeah, I try to be slow and fit in my time. It's impossible. Okay, another impossible mission for today. So today I'd like to talk about a pretty unique model we use in neurosciences, and that's the primate. And I'd like to convince at the end why we need primates for our research, for some of our research at least, before we end up with the clinical trials. And first of all, I'd like to acknowledge my colleagues, especially the primate behavior pharmacology lab, a section of our translational neuroscience laboratory, and also the human psychophysiology lab, and collaborators at the Gedeon Richter Pharmaceutical Company, and some collaborators from Institute of Neuroscience, Behavior Science, and also a nursery home where we did conducted some experiments, and my great friend, Professor Kenichiro Tsutsui from Japan, who we did a lot of thinking in the past 20 years on behavior neuroscience. Okay, so we do translational neuroscience, and this is a kind of a new, a pretty term in neurosciences that whatever we do, whatever technique we develop should be somehow connected to the clinics and should aid the benefit of people and the cure of diseases. And we can also think in a forward translation way where the techniques of let's say less complex species resemble or maybe as similar as possible to the techniques used in humans and lead to comparable results, cross-species evidence, as we say in a PC way in neuroscience. And we also look at the clinic, what results in clinical trials and clinical experiments we see, and we try to take them back as when we find unmet medical needs, and we develop new techniques and new tools. It's especially the case in behavioral neurosciences when we try to address a really complex and really unknown level of cellular organization, the way the cells are connected into assemblies, and these assemblies lead us to have a perception of the world around us and inside us, and the complex of the two. And then we are aware of our environment, we have consciousness, and then we try to focus on things, on stimuli, we have attention, then we try to match the information which happens to arrive in the brain with information which is already stored in the brain with memories, and then we try to make decisions, and finally we put those decisions into action. So if we think of all these, this is a greatly complex process, and still we have to model it somehow in the lab to be able to aid the research in the clinics. So what we do in our lab, our mission statement, you may already have read that, is to develop new techniques and also to validate techniques to make them available for example, drug development in rats, non-human primates, and also in human volunteers. And we test cognitive domains, mainly attention, working memory, and some complex memory and decision-making processes what are really unique to primates. And we introduced a few research tools in the lab in the last 10 years. We vary the task difficulty. That's a natural model of forgetting. You will see that in a sec. And then we also try to work with aging subjects if we have them available. And we also test the effects of natural aging on task performances. And we also use what we call pharmacological amnesia models, which are an easier subset of the models for cognitive research, but still are maybe very useful in preclinical sciences. So we have a very simple and maybe for some of you already outdated model of the human cognitive information processes. So as you see, a myriad of information enters the brain, and then we select some of those. We cannot process everything at the same time. It's impossible. And that is called attention, and then we put this information into some buffers, so they are available for a while, for like fractions of a time, like seconds, and then we encode them. We put them in another storage box, let's say, where they are available for instant use and decision making and selection from the stimuli for our benefit. And then, of course, we need to store some information for good, for later. And then while we are making decisions, we have to be able to retrieve information from these long-term storage boxes. This looks like a computer. So these are the buffers here, and this is like the random access memory, and this is like the hard disk. So we work with a really fascinating computer, our brain, and probably the computers we use now and with us every day, they are kind of extensions of our brain, simplified versions of our brain. So let's see how can we make this approach to this really unknown and really complex system kind of handful. So first, we developed a paradigm what addresses the first subset of information processing in the brain, which is attention. So this is a pretty simple task. It's called the psychomotor vigilance task. This was not invented by us. This was invented in the 50s and was used everywhere, even in the space. So this really nicely measures what we call sustained attention and alertness. How long you're able to keep your attention focused on very boring things. So you see this is a dot here, and whenever the dot appears, you are alerted and you press a button. Or we twisted it a little bit, so we put a warning stimulus, a dot, and whenever the color changes of the warning stimulus, you press the button. And you do it like for like an hour, which is that boring. And sometimes you fall asleep. It's a kind of a micro sleeping. You don't even notice you sleep. And that's the dot, I press the button. And when we analyze the data, it's like 5, 6, 7, 8 minutes of lapses. Seconds of lapses. So you imagine you drive a car on the motorway with a speed of 140 kilometers per hour, and for 5 seconds you have a blackout. It can cause death, and it does cause death. This is one of the major causes of death on the highways, on the motorways, when you have lapses. So when we are tired, this task is very sensitive to tiredness, and also it very nicely measures what we call time on task, how vigilant you are, how alert you are. And then we try to translate this task between humans, primates, and also rats. I won't show you the rodent data. Today, I focus on human and primate studies, how we address preclinical research in this field. Okay, so, oops. Something happened. Oh, that was me. Okay. So we put the task in the lab, and then we developed the primate version. So here's the rhesus monkey. He works in the task, he sits in a primate chair, and whenever he sees the color change of the dot, he releases his button and gets a very nice piroshka juice, which is nice. He likes it, it's nice. Okay, so what you see is really astonishing. These are the humans. So humans have a very nicely comparable reaction time to monkeys. And also this task, you see, is pretty resistant to time on task, so working in the task for like 20 minutes. We didn't test that in monkeys, especially before and after, but continuously. We also see the same mean reaction time. And also what we see here, the longer you wait for the target stimulus, the faster you become. And that's what we call the 4-period effect. So that's kind of a winding up of the brain. It's kind of priming, so you're really waiting. So you're developing we think a short-term memory on a stimulus that should occur now. And then, because the task is answer the button as fast as you can, you become faster. So this is an entrainment in brain oscillation also, but I'm not talking about that today. So what you see here, but then we go into a common method of pharmacological validation, so we can cause amnesia in these animals by giving them a drug. This is scopolamine. That's a drug that's an antagonist, non-specific muscarinic acetylcholine receptor antagonist that covers the receptors of the cholinergic system also in the brain. And these animals have like 1 or 2 hour difficulty in paying attention, and also some of the memory functions, as you will see. Now we tested the effect of this drug on attention, and you see this is the normal response of the animals. This is the response on the scopolamine. So they are motivated, they do the task, but they are slow. And also they completely lose their 4-period effect, so they are not becoming faster while they are waiting for the target. And then we give the Alzheimer's drug, donepezil, which is a cholinesterase inhibitor. It's a pretty old stuff, but we don't have any better, so that's why we are doing drug development. And then you see that this drug partially recovers reaction time, but it doesn't really recover the temporal expectation. So it does something to attention, but it doesn't do what we would like it to perform on this expectation effect, so this type of memory effect. So then we have a question, okay, we are pretty well off in the lab with this task, so how does it look like in real life? So we were very happy because a nursery home offered some opportunity for us, and we said, okay, we go there and we play this task with the inhabitants. And these elderly people, they were very happy to participate, and we explained them what we do and how we do the task. And okay, let's play. And as you see, these are the university students, so they are kind of fast and accurate, and they become faster. And these are the elderly people without neurological records, so they didn't have stroke or any other neurological diseases. So they are slower, but they also have this expectation effect. So this is okay. So we have a natural aging slows us down. We know that. Fine. And then we went on and we tested a few subjects, a few volunteers who already had some cognitive impairment. So they were prodromal Alzheimer's disease patients. So they have mild or moderate neurocognitive impairment. And as you see, they became slower and slower. So this curve is this curve here, slower and slower, and they almost completely lost their 4-period effects, so their expectation. So now we have at least one measure of this task, which gives us room for testing new drugs and for putting this model into drug development. And the more severe the symptoms they had, according to some pen and paper scaling, the worse they were in this task. So this is kind of a complete translation of a task, a phenomenon from the primate lab into the real life, and also hopefully in the clinics. Now I would like to show you 2 more, if I have time. I'd like to show you 2 more tasks which are not completely developed, but they are at some stages of development. So this task is called delayed matching to sample. This tests working memory, what we call, so short-term visual memory. So we are shown an object, and and there's a delay. We have to remember this object, and after a delay, we have to choose this object from many distractors. So first we measured the task, validated with our university students. They were happy to participate. And what we saw here, these are the humans up and down the NHPs, the non-human primates. They are strikingly similar even if there's a delay condition, short, medium, long, or with a short delay there's a distractor condition, so small amount, medium amount, and high amount of distractor stimuli, nonsense stimuli. So then we were convinced, okay, this is a good task, and put it into the test. So we did the same thing. So we used the scopolamine amnesia. Actually, this is a monkey performing in this task. So you see they are pretty clever. This is the end of a trial. So this is a trial. So you remember this and then choose from 3. Okay, good. Get a reward. Nice pellet. Okay, fruit flavored pellet. They love it. And again, choose. and again, hit. It's no problem. So they are pretty clever. And then they receive scopolamine, and as you see, their memory performance declines, but it especially declines in a 10 to 15 second delay, and it doesn't decline in a short delay. So this drug affects attention and affects especially short-term memory in the medium delay range. And then we gave donepezil, and memory came back partially because that drug works to some extent, but it's not doesn't perfectly recover memory. And then finally, in the last 5 minutes, if I still have some time, I'm checking my watch, not too much, but in the last 5 minutes, I'd like to introduce a really unique primate object memory, object location memory, working memory task, which cannot be done by any other species. But astonishingly, primates, and probably in our lab, first time in the world, they even outsmarted humans. So the task is not so simple. So you have to remember the position of this stimulus and another one, another one. We can increase the number to infinity, but that will be a breaking point, of course. And then there's a little bit of delay, like a few seconds. And then every single stimulus is shown at every possible position, and you have to choose the right position for the stimulus, what you remember. And then you only get a reward if you do the sequence right. So I show you how a monkey works in this task. This is a three stimuli in 3 positions. Okay, so this is one. I acknowledge. Good, and then delay, and then it was here, it was up there, and it was there. Great, reward. And then another trial. This looks like a really genius monkey because he can remember 3 objects at 3 positions. Good one, good. Okay, please try to remember. And you still remember? Good. Well, excellent. As he scans the screen and got it. Okay, you think the monkey is clever. Well, you see the same monkey a year later. Okay. Good lad. Can you follow? Because I can't. This is a shame on us, human beings. This is really difficult. So when we do this task with our volunteers, like you students, of course, probably with this amount of practice, you will do the same well. But without practice, or with practicing for like 1 or 2 days, it's not possible to choose like 6, 7 objects from like 7 to 9 locations, because we even make the task difficult by putting into nonsense locations, which were not there in the sample phase, because monkeys were too good. And we had to make the task difficult. Okay, then you see that monkeys are not so good. Humans, the black dots are okay, much better. Monkeys are the color dots. And then after some time, like half a year, monkeys caught up, some of them, but then all the monkeys caught up, but I don't have that figure with me. And the humans really deteriorate when we increase the number of stimuli. So then what are humans better than monkeys in? So maybe they generalize better. So we put new objects in, and we saw, the monkeys don't perform. Good, humans are better. But after a week, for the second presentations, the monkeys were better. And then after a week, for the third presentation, the monkeys recovered completely. So this natural forgetting model of putting new objects in and thinking that monkeys cannot generalize the objects, this failed. So then we went on. Then we were really evil. So what we put in the same object. You see this object, for example, in the next trial, but in a different location. And then we won. You can see the monkeys were really bad at doing the task if the same object was put in a different location in the next trials from the preceding trial. So then it's good. Then we tested this for a whole year, whether the monkeys can learn. And as you see, when we put in this interference stimulus, then the monkeys performed really bad for a whole year. So then we said, okay, we have a task. Now monkeys are just as bad as humans in this interference. You can imagine this is a really difficult situation when you just have something in your short memory. You even get a reward for that, and then the same thing appears a little bit somewhere else, and that's a complete disaster. And And then we put the test into the scopolamine model, because that's the next step. And you see that when we have the strongest interference, a stimulus from the preceding trial, then the amnestic agent acts with the highest intensity and impairs most the performance. So this is where we are at the moment. So we have pharmacological amnesia and natural forgetting models in primates of human cognition, and we think that the within trial length in the psychomotor vigilance task and in the normal short-term memory task is a good measure, so we can use it for drug development. And in the PAL task, the pair-associated learning task, we have the interference paradigm, which is really unique. It's a natural forgetting model, and we think that we can have that for the future. And we think that these models, which are really unique to the primate world, will help us in the development of new drug candidates, and at some point they will help us to speed up disease-modifying, the discovery of disease-modifying agents in pharmaceutical research. And I finish with this picture, which is from a science interview or Nature interview from 2014. I didn't know, but that was an interview with where also Professor Botond Roska has some thoughts about the new phase of primate research, and it was by chance. Thank you very much, and thank you for the intriguing and fantastic lecture of Professor Roska Botond, inspiring us. Okay, thank you very much, and that was it. Some other projects from our lab, but if you're interested, please approach me, and this is it. Thank you very much for your attention.
Thank you very much for this enthusiastic presentation. And now the floor is open for discussion, and we are waiting for questions from the audience. First of all, there is a question there. I'm very happy. Please speak out.
What I would like to ask is, you mentioned inducing amnesia on some of the experiments, and I am interested in how the prolonged use of these drugs alter further experiments.
Excellent question. Thank you very much. This is a question we ask in the lab every day, almost. What you experience, they get used to the drug. So the more often you do the experiment, you have to increase the dose of the drug, which is not so great. So that limits the experiment. Actually, it doesn't really rewire the brain or has any ongoing effects or takeover effects. So if you use the drug on day 1 and you test the animal on day 2, you see nothing. So it's complete. It's a very nice washout. It's like, I cannot tell in this audience, of course, because first I'm not paid for that, and it might even be illegal. But you take some drugs, all of you, which has a very very good washout, and the next day you're just perfect almost. Well, if you don't take too much. Of course, if you take too much, then we have issues. Yeah. So these drugs are commonly used mostly in rodent research. And some of them are used also in primate research, but they have a very good washout. Yeah. Thank you. Very good question.
Any other question from the audience? There is one at least.
Okay.
Lady in the middle, please.
We were just wondering, does the reward impact basically the efficacy how birds can match? So the monkey got the reward instantly, but the human obviously didn't get food when he cared for it to match perfectly. So does this kind of rewarding affect motivation or the accuracy which maybe so just talked about?
Amazing question. Thank you very much. Motivation and rewarding effects and accuracy, they have some I'd say connection between correlation, but not too much. So motivation can be completely dissociated from accuracy. So you can be accurate and motivated for like 5 minutes, no problem. So some monkeys, they are motivated for 10 minutes, they are accurate like that, and then they stop working. Or you can do this in a very low level. You just press the button or press the stimuli, bang, bang, bang. And you think, okay, Yeah, I can do it like 25%, I get rewarded 25% of the trials, fine, who cares? And then they go home and, give me my lunch. So it's like that. And then we say, okay, we give you lunch, but not that much. Okay, next day I work a little more. So we play around with that a little bit, that's true. But motivation and accuracy, yes, they have some effect on each other. And that can be because we have dopamine, which is a very nice signal of reward in the brain, and also dopamine aids a little bit of memory also and accuracy. But that takes us to another a really new word and really excellent. Thank you for the question.
And maybe a last short question from the audience somewhere.
Is there any scientific explanation for that? For this fact that most of these short-term tests, mostly the primates had a better result
than humans? Oh, excellent. It's another great question. Thank you. Well, actually, it's evolution. The answer is evolution. So primates are evolved to live in the present. So if you, you can look up videos like Kyoto Primate Research Center. Monkeys are playing this type of short-term memory task. They clearly outsmart humans. So they can remember a sequence of 15 different objects, and they remember the location of these 15 objects on the screen in 200 milliseconds, and they are happy to give back even the sequence. That's really crazy. And if you take a little child, like 10-year-old child, they are the best in this type of visual working memory. They can do like 7, 8, 9. I'm happy with 5. So yes, that's evolution. This is how our brains are wired. So human brains, we live in the past and the future. So the present, it doesn't really matter. So whatever we do, we think about the past and we try to predict the next moment, the future. The longer we can predict, and better that we can predict the future, the better we survive. Monkeys, they don't really care. They have to live in the present, and if we can see the difference of the wiring of the brain, that would be great. But I'm not sure there are any scientific results for that really tiny difference of the brain wiring. But yeah, great question. Thank you.
Well, for further questions, I think we have to wait for the break. But before we finish here, we still have a duty to hand over a certificate for you. So please come forward and we will hand over your prestigious certificate.